So on this last video, we're going to talk about the last property of water and then a little bit about pH. So the last property of water is that water is a solvent. So we've seen that water is adhesive, has high surface tension, how it changes states of matter, but the solvent. Solutions, so when we have things in class, in lab, mixed together, those are solutions. And usually that's created with a solvent and a solute. So for example, a solvent usually always is water, which basically means that things are easily dissolved into it. So think about things that might dissolve into water in your house. You might make a salt water. You might make sugar with water. You might make iced tea or lemonade or even some type of, let's see, um, instant coffee. So some type of dry or liquid solute mixes in with solvent really well and it creates a new solution. So solvent is the water, the solution is what we might mix it with. So here maybe this is salt water and we have salt as the solute and water as the solvent. So basically it's that polar and ionic compounds will dissolve in water because they are hydrophobic. They like water, so they'll easily mix together. So, salt water, salt and sugar, sugar and water, making kind of a simple syrup, things like that. Things that don't dissolve in water, though, are hydrophobic, and those are what we call nonpolar compounds. So examples of nonpolar compounds are lots of fats, lipid-based solutions. Like, so oil and water don't mix. We know that if we wanted to have a big pot of water on the stove and you put oil in it, because my grandmother, who was Italian, thought that if you put oil in it, that it didn't make the pasta stick together, whatever, the oil would sit on the top. It didn't mix through because oil and water don't mix because their polarities are different. Oil and fats are nonpolar and water is polar. So those are the types of things that will not mix well with water. So those are the kind of the anomalies that becomes water is a solvent, but they don't mix with oil or fats or lipid bases. Okay? Now, pH and water. Now, pH basically stands for per hydrogen. So per hydrogen that we might have. So on a pH scale, we have acids, we have bases, and we have neutrals. Now, acids release hydrogen ions, so they're going to increase hydrogen ions in a solution. Usually they're sour, and our most acidic is hydrochloric acid, which is the type of acid we actually have in our stomachs to break down food. Bases are going to take up the hydrogen ion, so take it in, or they might release a hydroxide ion, OH. They might get rid of this. Usually these are bitters, and our most basic is sodium hydroxide, which is like lye, which is very caustic as well. So we have what we call a pH scale, which indicate the acidity or alkalinity of a solution, so whether it's acid or base. And we have a range from 0 to 14, and 0 to 7 are our acids. 7 is neutral, and then about 7 to 14 are our basics, so our bases. Basically, this is an inverse scale, so if we're increasing hydrogen ions, then are decreasing the pH is what's happening. So it's actually a logarithmic scale based on 10, so 10 times. But this is a visual that's very helpful. So 7 here is neutral. It's in the green. That's basically our distilled water, or the water coming out of our tap should be neutral. And anything going this way, so 6 down to 0, basically, are acids. And then again, if we're at 8 to 14, those are our wonderful bases. So if we kind of look at this, this is our hydrochloric acid, lemons, vinegar, tomatoes, bananas. Anybody thought bananas were acidic? These, I think, are potatoes. A little hard to see right there. Again, would you think that those were acidic? So these are really common household things we have around. Again, in your house that are very acidic, and too much of them might not be a good thing. I don't know if anyone's had too many lemons at some point. They affect how your tongue and mouth are. But if we go the opposite direction, 8 through 14, here's our most basic. Eggs baking soda. So these are some examples of things we might eat, but the rest of these are basically household things. So soap, ammonia, bleach, oven cleaner, and this is lye. Lye is used in very small concentrations to make actual bars of soap. So it's very interesting. So this just kind of shows you the range of the two of them. Now, our body has things that are called buffers, and we use them in lab as well. And buffers basically are a substance that helps to kind of minimize any change in pH. So it kind of keeps our pH stable. The pH of our blood is 7.4, so that's pretty neutral. And we don't want to be swinging out of any range, but because of the way we break down some chemicals in our body, we can make things a little more acidic at times or a little bit more basic. So we have buffers in the blood that keep us at that 7.4. So carbonic acid is something that we have in our body, and it disassociates from bicarbonate ions. And when it does that, it has a hydrogen ion that's kind of released. So we want to make sure that we have a balance in between this acid and base range. Okay, so here is, again, our wonderful, okay, let me go back for a minute here. This is our bicarbonate, right? Bicarbonate ion. So bicarbonate ion is important because we have bicarbonate ion and hydrogen. That is what's broken down at dissociation. But we can add these two together and get carbonic acid again. So carbonic acid is an example of a buffer that we have in our body. So if our blood pH goes up, so the number goes up, it's considered more basic. What's going to happen is the carbonic acid is going to break apart, so the hydrogen ions will increase. And when the hydrogen ions increase, basically we're making this reaction go to the right. So right now, we are moving this direction. We're moving to the right when we have a high base, okay? And what happens is when we release this guy, our pH is going down. So bringing us back down to neutral. Okay, when our pH level goes more acidic, so it's below 7, what happens is this bicarbonate removes a hydrogen from here. And what we're doing is the reaction then is going to the left side, and we're going to use up this extra hydrogen ion floating around, and what's up happening is we're going to increase our pH from a little below 7 back up to 7. So it's an inverse reaction that's happening, and all we're really doing is worrying about this guy right here, that hydrogen ion. That's what we're worried about. And so that's pretty much all that we're going to worry about as far as pH is concerned. There is another video on our Moodle page that talks a little bit more about acids, bases, and pH that can help you and gives you just a little bit more information, heard in a different way, told in a different way, that will be helpful for you this chapter.